Welcome to Quantum Mechanics Unlocked. Today we will explore the superposition principle, the idea of being in two states at once. In the macroscopic world, things are either or. But in the quantum world, objects exist in a combination of all possible states simultaneously, the both state. Superposition means a quantum system is in every possible state until measured. Reality is a probability, described by a wave function. The act of measuring forces the system to choose one specific state. In part 1, we will compare classical versus quantum mechanics and see why Newton's laws are just the tip of the iceberg. Classical superposition involves wave mechanics. Classical waves, like water or sound, overlap to create interference, following a simple linear addition rule. Waves reinforce each other when peaks align in constructive interference, creating a larger amplitude. They cancel out when peaks align with troughs in destructive interference. In quantum mechanics, superposition applies to matter itself. An electron acts as if it is spread out in space, meaning it is truly in multiple locations at once, not just that we don't know where it is. Part 2 delves into the math of superposition, using the rigorous language of Paul Dirac and the concept of Bra-Ket notation. Quantum states are represented by Ket vectors, encoding all information about the system. This mathematical notation allows us to calculate how states overlap and interact. A superposition is a linear sum of basis states. The coefficients, alpha and beta, are complex numbers called probability amplitudes. Normalization dictates that the square of the absolute values of the amplitudes must add up to exactly 1, representing a total probability of 100% that a physical reality exists. Quantum states reside in Hilbert space, an abstract mathematical vector space. Every point is a possible physical state, and the dimensions correspond to the number of basis states a system can occupy. Part 3 examines the proof of superposition through experiments that shattered classical intuition. The double-slit experiment shows electrons form an interference pattern, even when fired one by one. This proves each electron takes both paths simultaneously as a superposition. The Stern-Gerlach experiment showed that particle spin is quantized and can exist in a superposition of up and down until the binary outcome is measured. The Mach-Zehnder interferometer demonstrates path superposition by splitting a photon and recombining its paths. Interference control proves the photon was on both paths. The quantum eraser experiment shows that if we mark which path a particle took, interference disappears. If we erase that information, the interference pattern reappears, even after the particle hits the detector. Part 4 introduces the qubit, the fundamental unit of quantum information, and how superposition is harnessed for the future of technology. Unlike a classical bit, which is either 0 or 1, a quantum qubit is exponentially more powerful because it can exist in a superposition of 0 and 1, processing all possibilities at once. The Bloch sphere visualizes a qubit state. Superposition states are points between the North Pole, state 0 greater than, and the South Pole, state 1 greater than. Quantum calculations involve rotating this vector. This exponential scale, known as quantum parallelism, means just 300 qubits can represent more states than there are atoms in the observable universe. Part 5 explores the paradoxes of superposition, where logic starts to bend in the quantum realm. Schrödinger's cat is a thought experiment showing the absurdity of quantum rules at the macroscopic scale, proposing a cat is in a superposition of dead and alive until observed. The measurement problem is the unsolved mystery of why observation causes wave function collapse. Decoherence, interaction with the environment, destroys superposition almost instantly. The many-worlds interpretation suggests no collapse occurs. Every possibility in a superposition happens in a separate, branching universe, meaning the superposition is never lost. Finally, Part 6 covers the impact of superposition, using the impossible to change the world. Quantum computing harnesses superposition to factor large numbers and simulate complex molecules in seconds, tasks that are impossible for classical supercomputers. Quantum sensors use particles in superposition for ultra-precision, detecting tiny changes in gravity, magnetic fields, and even neural activity. In quantum communication, if an unauthorized party tries to look at a quantum key in superposition, the state collapses, immediately alerting the sender of a security breach, making it unhackable. To summarize, the future is superposed. Our 3 key takeaways are: quantum systems exist in a weighted sum of all possible states simultaneously, measurement forces collapse, and superposition is the engine behind quantum technologies. Thank you for exploring the quantum frontier with us.